What is supercooling in thermodynamics? Have you ever wondered how a liquid can stay in its liquid form even when it is cooled below its freezing point? This fascinating phenomenon is known as supercooling. Supercooling occurs when a liquid is cooled below its normal freezing temperature without turning into a solid. This means the temperature drops below the phase change temperature, yet the liquid remains in a liquid state. The reason this happens is that freezing requires a nucleation point. This is an initial site where molecules can start to arrange themselves into a solid crystal structure. If there are no nucleation sites present, the liquid can remain in a liquid state, even below the freezing temperature. This state is referred to as supercooled. To better understand supercooling, it helps to know how freezing works. Freezing is a phase change where molecules in a liquid slow down and organize into a solid crystal lattice. Normally, this process begins at nucleation sites, which can be impurities, rough surfaces, or other particles. Without these sites, the molecules struggle to start freezing, allowing the liquid to stay in a metastable state called supercooled. In the context of thermodynamic systems and phase changes, supercooling shows how these transitions depend not just on temperature but also on how molecules are arranged and the conditions of the surfaces they are near. The liquid is in a non-equilibrium state because thermodynamics suggests it should be solid at that temperature. However, kinetic barriers prevent the transition from occurring. When a supercooled liquid is disturbed, such as by shaking or pouring, it can rapidly crystallize. This process releases latent heat as it changes from liquid to solid. The sudden freezing can be visually striking and serves as an example of how thermodynamic principles govern phase changes dynamically. A specific type of supercooling that is relevant to alloys and solidification is called constitutional supercooling. This occurs when compositional changes in a liquid during solidification cause the liquid temperature near the solid-liquid interface to drop below the freezing point. This can impact the stability of the solidification front and the microstructure of the solid that forms. Supercooling has practical applications in various fields. For instance, it helps us understand the formation of freezing rain, where supercooled water droplets freeze upon contact with surfaces. In food preservation, techniques using supercooling keep liquids unfrozen while at low temperatures. Additionally, in industrial processes, controlled solidification of metals and alloys can be influenced by supercooling, affecting crystal growth and material properties. In summary, supercooling in thermodynamics is a fascinating phenomenon where a liquid remains in its liquid state below the freezing point due to the absence of nucleation sites. It highlights the interplay between temperature, molecular structure, and phase transitions in thermodynamic systems.